This video is going to cover simplifying square roots and then using the Pythagorean theorem and the converse of the Pythagorean theorem. So the first part of this is a review of algebra. So this is how you would take a radical, like the square root of 216, and simplify it. So what you want to do with any radical is break it down into its factor tree. So you can see this 216 was broken down into its factors, and you could break them down in any way you want. You could do 2 and 108 and then keep breaking it down from there. So if you had done that, that would look like this. 2 and then 108. And then 2 is prime, so you'd stop there, but 108 keeps going. You can go 2 again and 54. 2 is prime, but 54 keeps going. This would be 2 and 27. 2 is prime, but 27 can be broken down into 3 and 9. And 3 is prime, but 9 can be broken down into 3 and 3. So then once you get to that point, you're looking at all of the dead-ended factors, so the ones that are prime. And you want to, because a square root is the result of a number being multiplied by itself, you want to find as many pairs of a same number as you possibly can. So if I have a pair of 2s, like here, I would bring that 2 to the outside of the radical. So anything that has a pair is going to the outside of the radical, and anything that doesn't stays underneath. So that's one pair of 2s, and then this 2 is all by itself. There's no other 2 to match it with, so that 2 is going to go underneath. I have a pair of 3s. That 3 is going to go to the outside, and then this 3 doesn't have a match. That's going to stay underneath by itself. And then however many numbers I take on the outside, I would multiply those together. So 2 times 3 is 6. And whatever's on the inside, if there's more than one number, I'm going to multiply those together, and I would get 6. So then here's my simplified radical. 6 times the square root is 6. This second example has a square root in the denominator. So we can't leave a square root in the denominator. It makes our fraction what's called irrational. And so we actually have to do what we call rationalizing it, which is multiplying both the top and the bottom of your fraction by the square root that's in the denominator. So if I had 6 over square root 2, then I would multiply both the top and the bottom of this fraction by the square root of 2. Multiply straight across here, and I get 6 times the square root of 2. Multiply straight across here, and I get square root of 2 times square root of 2, which is the square root of 4, and that reduces to 2. So shortcut, any root times itself is going to be what's underneath. So if I have root 2 times root 2, then I know my answer is just 2. And then from this step, I've got 6 root 2 in the top and over 2 in the bottom. If there is a number outside the square root in both the numerator and the denominator that can be simplified, you can. Same thing if there were 2 numbers underneath the square root. So if I had 6 root 2 over, let's just say 5 root 2, you can actually cancel out the root 2's. So in this case, the one that you see there in the red, 6 and 2 are both divisible by 2, so 2 goes into itself once and into 6 3 times, and from here I get 3 root 2. So what I can't do is simplify something outside a square root with something inside the square root. So I can't cancel out those 2 2's. My answer would stay like here, 3 root 2. So these next examples basically follow those patterns. Number 1, square root of 720 broke down into 10 and 72. 10 then breaks down into 2 and 5. Both of those are prime. 72 breaks down into 8 and 9. 8 then breaks down into 2 and 4. 4 into 2 and 2. And then 9 breaks down into 3 and 3. So then again, you want to bring them out in pairs. So I've got 1, 2 2's. That's 1 2 that goes on the outside. Another pair of 2's here brings another 2 to the outside. A pair of 3's here brings a 3 to the outside. And then the only prime number left is 5, and it's by itself, so it stays underneath the square root. So then I multiply 2 times 2 times 3, or 4 times 3, which is 12. Simplified, this would be 12 root 5. Number 2 has both the numerator and the denominator under your square root. So when you split them, it would get root 3 over root 16, like you see here. And then the square root of 16 can actually be simplified into 4. And now I've eliminated my square root from the denominator, and I don't even have to rationalize it. Number 3, 10 over root 2. Remember, you can't simplify the root 2 into the 10 because one's got a root, one doesn't. So I would multiply both the top and the bottom by square root of 2. 10 times root 2 is 10 root 2. Root 2 times root 2 is just 2. So I would have 10 root 2 over 2, and then 2 goes into 10 5 times, and my answer would be 5 root 2. 4, same thing. When you split this, it becomes root 1 over root 3. You can actually simplify this root 1 so that it would be 1 over root 3, but it won't change your answer, because then you'd still have to rationalize and multiply both the numerator and the denominator by root 3, and I'd end up with root 3 over root 9. Root 9 is actually 3. And 5 is just like the first example. We're back to square root. So we want to break this down into its factors. 45 is 5 and 9. 9 breaks down to 3 and 3. There are 1 pairs of 3, so the 3 goes to the outside, and the 5 stays underneath. All right, that leads into the application of the square roots, which is Pythagorean theorem. So in a right triangle, so 1, it has to be a right triangle, and 2, you have to have 2 of the 3 side lengths. The Pythagorean theorem says that a squared plus b squared equals c squared. Now, what's important here is the location of c. A and b are actually interchangeable, but c is the side that is opposite the right angle, or the largest side. So when you get given either 3 side lengths, or you're given, or 2 side lengths, sorry, or you're given the triangle itself, whatever's opposite the right angle, or the longest side goes where the C is, and then the other 2 can be flip-flopped. That doesn't matter. So this works you through the proof of where that comes from. Don't worry about that as much as applying it to your actual triangles. So an example like this just says find the value of x and then give your answer in simplest radical form. So let's work through this example. So C, again, is opposite the right angle, which means that x in this case is C. So I can say that 6 squared plus, not to the fourth, 6 squared plus 4 squared would equal C squared. 6 squared is 36. 4 squared is 16. 36 plus 16 is 52. And then to solve for C, I'm going to square root both sides. And normally we put a plus and minus in front of this if we're solving for algebra. But because we're talking about a side length, no side length can be negative. So I'm going to keep it as just the square root of 52, sorry. So C equals the square root of 52. And then I want to take 52 and break it down. So this is 2, 26, 2, 13, and then 13's prime. There is 1 pair of 2's here, so the 2 goes to the outside, and the 13 stays underneath the radical. And there's your missing side length. B, this time you actually have an expression on one of your side lengths. You still want to start the same way, identifying C, so opposite your right angle is C. In this case, it's x. And then the other 2 are 5 squared, so I would say 5 squared. Plus x minus 1 squared equals x squared. And then we want to solve this. So x minus 1, well, 5 squared is 25. X minus 1 squared, biggest mistake made here is to distribute this. That's not the way this works. This would be x minus 1 times x minus 1 equals x squared. And then I would FOIL out my polynomials here. So 25 plus x squared, outer negative x, inner negative x, and last positive 1. Combine your next like terms on the next line. So 25 and 1, positive 1 would be 26. There's only 1 x squared, so it stays as positive x squared. And then there's 2 x's, negative x and negative x, which becomes negative 2x. So then I want to work to pair up my x squareds here. I would subtract x squared from the left and from the right, and it actually cancels from here. So I have 26 minus 2x. And it cancels from here, equals 0. Then I want to isolate the x. So I have choices. I can either subtract the 26 and then divide by negative 2, or add the 2x so that the x becomes positive, and then divide both sides by 2. And you found your side length. All right, so these two just work through the same type of example. For 1a, we identify c as x. So 4 squared plus 8 squared equals x squared. 4 squared is 16. 8 squared is 64. 16 plus 64 is 80. And then 80 breaks down to 8 and 10. 10 breaks down to 2 and 5, which are both prime. 8 breaks down to 2 and 4. And 4 can get broken down again to 2 and 2. So from there, you've got a pair of 2's here. That means 1 goes to the outside. A pair of 2's here. A second 2 goes to the outside. And then the 5 that's by itself stays underneath the radical. And I end up with 4 root 5. And 1b is just like the last example where we've got an expression. So 12, we identify x plus 4 as the c. So 12 squared plus x squared would equal x plus 4 squared. 12 squared is 144. X squared is x squared. And then we FOIL out the right-hand side. X times x is x squared. X times 4 is 4x. 4 times x is 4x. And 4 times 4 is 16. Combine those 4x's and we're here. And then you want to solve. So in this example, she subtracted 16 from both sides and ended up here. 128 equals x squared, or sorry, plus x squared equals x squared plus 8x. Subtract x squared from both sides. They cancel out. And you get 8x equals 128. And divide 128 by 8. And you get 16. So there are sets of values that work for these these triangles that are referred to as Pythagorean triples, which means that if I was given 2 of these 3 values, you can actually assume the third is true without having to do the work. The most common triples are 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25, and I would add one that is 6, 8, 10. So what this means is if I was given a right triangle and this is 3 and this is 4, I can automatically assume this is 5 without having to do the work. Now be careful, because this does not mean that if this is 4 and this is 3, that the side over here is 5. Obviously, the side opposite the right angle should be your hypotenuse or your largest side. So if the 4 is there and not that 5, then this triple does not work, and you'd have to use the Pythagorean theorem to find it. So these are great to memorize. They're definitely going to be used on standardized tests. It will save you time. If you don't, then you've got to work through doing the Pythagorean theorem. All right, so A here says find the missing side length. Tell if the side lengths form a Pythagorean triple and explain. So the work here shows that a squared plus b squared equals c squared. The side opposite the right angle is the 15. So 12 squared plus b squared equals 15 squared. 12 squared is 144. 15 squared is 125. If you subtract 144 from 125, you end up with b squared equals 81. Square root both sides, and b is 9. So we just proved that this missing side would be 9, and that 9, 12, and 15, because they are all whole numbers, they are a Pythagorean triple. So you're looking to see if all 3 side lengths are whole numbers. If the 15 is not on the hypotenuse, like in this case, then 9 squared plus 15 squared becomes 81 plus 225, which is 306. And the square root of 306 is not 12. It would break down into your factor tree. So it would be 3 and 102, which is 2, 51, which is 3, and 17. So then from here, there's 2 3s. A 3 goes to the outside. A single 2 stays underneath. And a 17 stays underneath. And that leads us to 3 root 34. Because that's not a whole number, this is not a Pythagorean triple. All right, so this is the work for these examples here. For 3a, 8 squared plus 10 squared would give you 64 plus 100. Square root of 164 breaks down into 41 and 4, and 41 is prime. 4 breaks down to 2 and 2. This becomes 2 root 41, not a whole number, so it's not a triple. 3b, 24 squared plus b squared equals 26 squared. 24 times 24 is 576, plus b squared equals 676. subtract 576 from both sides, and I get b squared is 100. Square root of 100 is 10. That's a whole number, so this is a Pythagorean triple. C, 1 squared plus 2.4 squared equals x squared. 1 squared is 1, 2.4 squared is 5.76. And if you square root 6.76, that is not a whole number, so this would not be a triple. 3D, you're missing your hypotenuse. So 16 squared plus 30 squared equals x squared. 16 times 16, 6 times 6 is 36, that's 96, 6, 1, 256. So 256 plus 30 times 30, which is 900, there's 2 zeros. Add those together, I get 2, 5, 11. And then square root that. And this breaks down. So I know 2 goes into it. 2 would go into it. 5, 7, 6. 2 goes into that again. 2. 2 goes into 5. 2 times remainder of 1 into 17. 8 times into 16. 8 times. 2 goes into this again. 144. 2. 72. This keeps going. 2, 36, 2, 18, 2, 9, 3, 3. Got a lot of pairs, so that's one pair of 2s. That's a second pair of 2s. Third pair of 2s, and a pair of 3s. And then this 1, 2 that's left underneath by itself, which tells me this is not a whole number. So 2 times 2 is 4. Times 2 is 8, times 3 is 24 root 2. And this would not be a triple. Okay, the converse of the Pythagorean theorem gives you a way to tell when a triangle is right by knowing the side lengths. So in this case, if I know all 3 side lengths of a triangle and a squared plus b squared equals c squared, then I can prove the triangle is a right triangle. And it's important to identify that c squared would be the biggest of the 3 measurements. So if you're given 3 measurements, the 2 smaller ones would be the a squared and the b, or the a and the b, and the larger of the 3 would be the c. Plug it into the Pythagorean theorem and see if the equation balances so the left side equals the right. That's the converse of the Pythagorean theorem. The Pythagorean and inequality theorem also says that you can identify if the triangle is not only right, but obtuse and acute. So if instead of the c squared being equal to the a squared or the b squared, the c squared is bigger than the a squared plus b squared, then I know the triangle is obtuse. If the c squared is less than a squared plus b squared, then I know the triangle is acute. And remember, sometimes you get side lengths that don't even work for a triangle. The triangle inequality theorem told us that the sum of any 2 side lengths has to be greater than the third side. So oftentimes you'll get asked, do these angles or could these sides form a triangle? And if so, what kind? And that's where you'd make sure to check that. So this one says, tell if the measures can be the side lengths of a triangle. If so, classify the triangle as acute, right, or obtuse. So I want to look at 8, 11, and 13. Add 8 and 11, that's 19, which is bigger than 13. And then 11 plus 13 is obviously bigger than 8, and 8 plus 13 is bigger than 11. So I do know that this would form a triangle. Now I got to figure out what kind. So I'm trying to figure out what's the relationship between c squared and a squared plus b squared. Remember, I want the largest one to be the c squared, so 13 squared has what relationship to 8 squared plus 11 squared? 13 times 13 is 169. 8 times 8 is 64. 11 times 11 is 121. 169, add these two together, 5, 8, 185. This is less than, which makes this triangle acute. All right, B here says to do the same with the side lengths of 5.8, 9.3, and 15.6. This time when you add 5.8 and 9.3, you get 15.1, which is not bigger than the third side. So these cannot be the sides of a triangle. Here's some additional examples. So 7, 12, and 16. If I add 7 and 12, I get 19. That's bigger than 16, so this works. Now I got to find the relationship between 16 squared, 7 squared, plus 12 squared. 16 times 16, we just did this on the previous slide, is 256. 7 times 7 is 49, and 12 times 12 is 144. So 144 plus 49 is 193. 256 is bigger than 193, so this is an obtuse triangle. For B has 11, 18, and 34. So if I add 11 and 18, I end up with 29. That's not greater than 34. So this is not a possible triangle. For C, 3.8, 4.1, and 5.2. So 3.8 plus 4.1 is 7.9. That's bigger than 5.2. I'm trying to figure out what relationship 5.2 squared would have to 3.8 squared plus 4.1 squared. So let's do 5.2 times 5.2. Multiply it, ignoring the decimals at first. So add the 0, 26. And then because there's 2 digits behind the decimals, I move so that there's 2 digits behind the decimals. So this would be 27.04. I'm going to repeat that process for 3.8 times 3.8. 8 times 8 is 64. 8 times 3 is 18. Nope, sorry, 24 plus 6, 30. 3 times 8 is 24. 3 times 3 is 9 plus 2 is 11. And 2 decimal behind, 14.44. And the last one, 4.1 times 4.1. 1 times 1, 1 times 4, 4, 16. And 2 digits behind again, so 2 digits behind. So I want to add these together to see if they add up to be greater than or equal to or less than the one on the left. And I get 31.24. So when you compare 27.04 to 31.24, it is less than it, which means that this is an acute triangle. All right, so this is just a review kind of going through Pythagorean theorem. Number 1 says to find the value of x. So it's worked out here for you. Opposite the right angle would be the x plus 3, which makes that the c. 9 squared plus x squared would equal x plus 3 squared, which is here. 9 squared is 81, which is here, plus x squared. And then you FOIL out the x plus 3 squared, and you end up with x squared plus 6x plus 9. Subtract 9 from both sides, and you're here. 72 plus x squared equals x squared plus 6x. Subtract this x squared. They're going to cancel from both sides, and I get 72 equals 6x. Divide both sides by 6, and I end up with x equals 12. Number 2 says an entertainment center is 52 inches wide and 40 inches high. Will a TV with a 60-inch diagonal fit in it? So you've got a box, 52 inches and 40. And you want a TV with a diagonal of 60. So you want to know if it's possible for this side to be 60 degrees. So I could set this up like it's a right triangle. It doesn't matter if I pick that one or this one. 40 on the left means 40 is also on the right. 52 on the bottom means 52 is also on the top. So the question is, can I get 60 squared, which would be the c, to be less than 40 squared plus 52 squared? Because that would be the biggest measurement across I could have it. So 60... It actually could be less than or it could be equal to, because then it would make it a right triangle. It just can't be obtuse. If it was bigger than 90 degrees, it would bring it outside of the entertainment unit. So you're looking for it to be less than or equal to. So 60 times 60 is 3,600. 40 times 40 is 1,600. And 52 times 52, the works of is 2,704. So 3,600 has what relationship to? If we add these together, I get 4,304. Since it's less than it, I know this is actually going to end up being an acute angle, and it would work to make sure that it would fall inside that TV. So it actually will fit. This is a yes, and it will fit because that triangle would be an acute triangle, which is smaller than the right triangle that would, or the two right triangles that would make the entertainment center. All right, 3 and 4. 3 says find the missing side length. Tell if the side lengths form a Pythagorean triple. So I've got 5 and 12. This is a right triangle. 5 squared is 25, which is here. 12 squared is 144. Add those together, I get 169, and the square root of 169 is 13. Because those are all right whole numbers, this is a triple. Number 4, tell if the measures 7, 11, and 15 can be the side lengths of a triangle. If so, classify the triangle as acute or obtuse. So if I add 7 and 11, I get 18. That's bigger than 15, so I know it can be a triangle. And then I want to find the relationship between 15 squared and 7 squared and 11. So I would flip it so that it says 225 is what relationship to 49 plus 121. And 225 is greater than 170, which makes it obtuse. For me, I like to put the C on the left-hand side because I think it's easier to relate it that if the C is bigger, it's obtuse, and the C is smaller, it's acute. And that wraps up everything you need to know for this section, the review of square roots, Pythagorean theorem, and the converse of the Pythagorean theorem.